So I'll talk about the paper Generalized Coherent States in QCD from Asymptotic Symmetries. So I'll start with the motivation. Okay, so the conventional scattering amplitude in 4 dimensions suffers from IR divergences due to massless particles in the theory. And for abelian gauge theories, Faddeev and Kulish have proposed a formalism to construct infrared finite scattering amplitudes. So by considering the asymptotic states as dress states. And recently it has been observed that these dress states okay. So recently it has been observed that these dress states, they can be derived from asymptotic symmetries. In this talk I'll be explaining how to derive the dress states in QCD from non-abelian asymptotic symmetries. So for this we will use the key assumptions in the case of QED. Okay, so I won't be deriving the Faddeev states in QED directly from dress states. Instead, I'll show that the Faddeev states in QED, they satisfy Ward identity, and from that analysis, so basically we'll extract the key assumptions. Then using those assumptions, I'll try to derive the dress states in QCD from asymptotic symmetries.
Sorry, the dress states for Faddeev-Kulish were the states for which there were no further infrared divergences, right?
Yeah, QED, yeah, that is.
Is there a claim that there are such states also in QCD?
So yeah, there is a construction by Catani and all. So they call this generalized coherent states. So I'll be deriving exactly those states, but those states can't kill the collinear divergences. Only the leading IR divergences.
Okay. So they're not good scattering states. This is like a
no, because they can't anyway kill the collinear divergences.
Yes.
Okay, so.
And so even in n equals 4 angles, you have the same.
Yes.
This is not related to confinement. It's just non-abelian.
Okay, so first I'll explain about. I'll give a brief introduction about asymptotic symmetry. After then I'll explain about I'll explain Faddeev states in QED, and then so the dress states in QCD. Then I'll just summarize. Okay, so I'll just give a brief introduction to asymptotic symmetries. Asymptotic symmetries generated by gauge transformations where the gauge parameter do not die down to infinities. So for example, just consider the case where the gauge parameter that becomes an angle dependent constant at infinity. So this is the case we will be interested in. And unlike small gauge transformations, there exists a non-trivial Noether charge. And the Noether charge depends upon the gauge fields and the matter current which survives at infinity. So this is the expression for the Noether charge. So here, so this part is known as the soft charge, and this part is known as the hard charge. So here, so this integral is over the Scri plus, which is null infinity, and so we'll be working in UR Z bar coordinates. So and this alpha is the gauge parameter, and AZ and AZ bar, so those are the gauge fields which survives at infinity, and this Ju is the matter current at infinity. Okay. Yeah.
And gamma is the metric current?
Yeah, gamma is 1 by Z bar.
So you are assuming there are massless matter that is reaching at Scri plus, is it?
Yeah, it is massless case.
So Ju is just massless part?
Ju is just the massless part. Sorry, yeah, this case Ju is just the massless.
And you could also have massive particles, or you are assuming there are no massive particles?
So the thing is, the action of the hard charge and soft charge is, the action of hard charge, the action is same for the massive case. So the action is the same. So in this introduction, I will be just introducing only the massless case. So one can use go to the null infinite, sorry, I0 and sorry.
I plus.
Yeah. I plus and
For passing particles, you have to go to the.
yeah. So here I will be explaining only the massless case. So yeah, so if you consider the hard charge, yeah, so J is the matter current. So just to get a feeling for hard charge, so for constant alpha, then the soft charge, okay, sorry, yeah, so for constant alpha, the soft charge vanishes, and okay, and the total, the Q hat, it will be just the total electric charge, which is just sum over k EQK, where sum is over the it's over all the other particles. And so in the case which we are considering, when the gauge parameter becomes an angle dependent constant at infinity, so then the action of hard charge on an external state, it is given as follows. So basically here the K1 into K2, Kn, they are basically the moment of the external particles, and alpha is the gauge parameter. So you can think of this as the total electric charge, which is weighted by a gauge by a function. And here this Zki and Z bar K by Ki. So basically these are in the these are the Z bar coordinates in the momentum space. Okay, so then so for the rest of the talk, actually I will be choosing a particular gauge parameter. So for this particular choice of gauge parameter, so I can write the action of Q hat on external state as follows. So here basically where this S0 is known as the soft factor, which is a function of the external momenta Ki, and basically here this Ki, so this momenta can be parameterized in terms of the Zk and Zk bar, and the momentum P, it can be parameterized in terms of the W's. Yeah, so I will be using expression for this S0, sorry, I will be using this expression for the Q hat in the rest of the talk. So, and as you are asking, so the even for massive case, this action is the same, it is just S0.
So this you get from this 1 over Zk minus W, this factor epsilon W.
So it's not exactly that. So basically, yeah, there is an extra factor also.
But if you just choose alpha to be that,
Yeah.
then hard charge will just become EQKI times 1 over Zk minus.
Yeah, that is true, but that is not exactly S0. So basically S0 is, there is a 1 plus Z bar in the numerator. So with that factor it is S0. So just for convenience I am choosing this hard action to be like this.
Okay, so you just normal, really normal, put some additional normal.
Yeah, additional normal. Okay, so yeah, this is the story of the hard charge.
Where did the P come from the last time?
Yeah. So P, this coordinate W, so P is parameterized with a W momentum. Sorry, W coordinate here. And similarly also this polarization, this can also be parameterized in terms of the W's. Okay, so yeah, this was the soft charge. So here, when you quantize the operators, then the action of soft charge, so it's just this factor. So basically the soft charge, it creates and annihilates soft photons. Okay, so then also the Ward identity associated with this asymptotic symmetry, they give the leading soft photon theorem. Fine, so this was a brief introduction to the charges in asymptotic symmetry. So we will be using this soft and the hard charges, the action of those in the rest of the talks. Okay, so now I will explain about Faddeev states in QED. Fine. So, in the usual definition of asymmetries, we assume that the interaction will die down to infinities. Okay, and in that case, the asymptotic states, they behave like states of free theory. But in the case of QED, like in the case of long range forces, we know that this is not true, and the states are not free. And Faddeev and Kulish have showed that such states, they can be thought of states in the Fock space dressed with a cloud of soft photons. And yeah, so this is basically this MFK is the okay. Fine. So this MFK, this is the Faddeev-Kulish amplitude. Okay, so MFK is the Faddeev-Kulish amplitude, and S is the usual Dyson asymmetrics, and the these states are the dressed states. So here, okay, fine. So here I have given the explicit expression for the Faddeev-Kulish state. So this out is the, these are the states in the Fock space, and okay, so inside this operator, this A dagger and A, those are the creation and annihilation operators for the photons, and Q is the momentum of the photon, and Ki is the momentum of the external particles. So basically you can think of this state as coherent state of photons such that it has the information about the external particles also. Also there is a cutoff for the photons. So basically which says that this integral consists of only low energy photons, and yeah, so
this integral is over some form momentum Q, or
yeah, this is the Lorentz invariant measure. Lorentz invariant measure. Yeah.
And so, and the form momenta are integrated from 0
to some cutoff.
To some cutoff.
You are not in a force-based dimensions.
It is d4 q by
Q by 2.
Yeah.
Q by Q.
It is in four space.
It's not only on-shell photons. D cube K over 2K over.
Yeah, is it D3 Q over 2E, or is it D4 Q?
Okay.
With Bayesian analysis and operator, you will probably introduce only for the on-shell.
Yeah.
So D cube K over.
Probably D3 Q over 2E.
Okay.
And then the cutoff is all mod of it.
Yeah.
So it will also be tricky what is cutoff.
What happens to the lofty term, like rectangle area? That has not to be taken into account.
Sorry, what?
In force spacetime dimensions, you have this long range force. For that also you need to take into account.
The second part of the Faddeev-Kulish test, the Coulomb force.
Oh, yeah. So, okay, fine. So, yeah. There is a Coulomb part also. So, which actually I haven't taken into account here. So, which I just assume that goes inside this asymmetries. There is a imaginary part also. So, this is only the real part of the address states. Okay.
Would you say that this phase is not important? So, because that phase will not be particle by particle.
Okay, the thing is, our goal is to derive this part of the dressing from the asymptotic symmetries. So that is why right now I am not considering about the Coulombic part. It's actually there. So basically I am just considering it to be inside the asymmetries.
So in principle, the Coulombic part can also be derived from asymptotic symmetry?
No, it can't.
So this is the real photon.
Yeah, this is only the real part of the dressing. So also, and they further argued that the asymmetric elements in this dress state, this MFK, they are IR finite. So basically what happens that the IR divergences in the coming from the S matrix that cancels with the IR divergence in the dress states. So that is how this MFK becomes an IR finite. Okay, so yeah, so this was the Faddeev construction for the states. Okay, so next I will be explaining. So next I will show that the Faddeev states, they satisfy Ward identity, and so from that analysis I will try to extract the assumptions about a few assumptions, and using those assumptions I will be deriving the dress states in QCD from the non-abelian asymptotic symmetries. Okay, so for that purpose, consider the Faddeev states. Then okay, then so now I am going to consider the Ward identity in these Faddeev states.
So e to the minus r out is this operator, is it?
Yeah, so e power minus r out is just this operator. So here similarly there is a dressing operator for the in state also, which is just e power r in. Okay, so yeah, so now I am going to consider the Ward identity, and I am going to show that the Faddeev states, they actually satisfy the Ward identity. So yeah, so as I was saying earlier, the charge can be decomposed in terms of soft and hard charge. Okay, so then if you consider the action of the soft charge, so basically the soft charge, it can act on the dressing operator, which is given by this factor, as well as it can act on the external state. So essentially the Faddeev states, so these are not the eigenstate of soft charge, and there is an extra conclusion coming from when Q soft is acting on the external state. And yeah, so this is exactly like the Q soft, it basically when it acts on the external state, it shifts the vacuum. So this is precisely that contribution. And yeah, so then if I consider the Ward identity involving the soft charge, so basically it will have so these 4 terms. So these are exactly the commutator terms, the first one and the second one, and these are precisely these kind of terms. That
so when you say that it shifts the vacuum, what you mean is that like it's adding like a soft.
Yeah, it is adding a soft photon to the external state. So basically the vacuum is infinitely degenerate because of the presence of the soft charge. Yeah, so this is the this is the part which is coming from the action of the Q soft. And so the thing is that, I mean, it is observed in QED that the Faddeev states, they actually satisfy a condition called orthogonality relation. So which says that so basically if you consider this state, this is the state which has one soft photon, and there is an dressed finite energy states. So basically which is just says that this state is orthogonal to all the other dressed finite energy states. So basically to prove this condition, I mean this constraint, yes, so using Feynman rules, one can actually show that this is indeed true. So then basically so then this extra soft photon, it can either be emitted from the external states or it can be emitted from the dressing cloud. So actually, so the emission of the soft particle from the external state, it is given by the soft theorems, and that part, that exactly cancels with the emission of the soft particle from the cloud. So that is how one can show that this actually 0.
Can you understand that?
Okay.
So are you saying that there are two terms now?
Yeah. So basically, this state, it consists of a one soft photon, and there is a finite energy rest state.
That's the 5 hours.
Yeah. That is the dressing the out state.
Yes.
So then, so this photon, it can either emit from the external legs, from the out and in states, or it can emit from the cloud. It can be connected to the cloud also.
Okay.
So when it is emitting from the external legs, so that is just given by the soft theorem, which is S0 is a soft factor. So yeah, that is exactly this contribution. So when the soft particle is connected to the cloud, so that is given by, so you can just use the Wick's contraction and you can get the result. So that is basically just the commutator of Q soft with this operator.
These two cancel.
Yeah, these two cancels. So basically this plus it can emit from the R in also, the in cloud also. Yeah, same boundary. So yeah, these two cancels.
Physically, is it clear what it means?
So okay, so in the usual formalism, people say that the Faddeev state is a eigenstate of soft charge. So that is the usual argument people give, but because of the presence of this extra term, that is actually not true. So because this is not 0, the Q soft shifts the vacuum state. So one can think of this state as null state. So basically it is orthogonal to all the other states in the theory because of this condition.
Faddeev state, it will never go into a state with one Faddeev and extra soft.
Yeah.
There is no decay somehow.
But suppose you have actual charge particle scattering, right? In the classical charge particle scattering, there is certainly soft radiation.
Yeah.
Is it clear how to get that result from this Faddeev description? Just target classical scattering produces soft photon radiation.
You mean by classical scattering?
Just two charge particles scattering, right? And use the standard classical formula, right? That has coherently photons coming out, right? And it's given by the soft, the usual soft, right?
Yeah.
So how can one reconcile?
It doesn't agree with or that agrees with this problem.
Yeah, I mean, if Faddeev Kulish is the correct formalism for the scattering, yeah, I mean, can you take the classical limit and get the classical scattering from there?
So you're saying it should produce the log, basically the log term, log omega.
Yeah, exactly. Log omega, I mean, in Fourier structure space, some one-body kind of waveform, right? Just classical scattering.
Okay. Oh, fine.
Even the memory, I mean, electromagnetic memory, right? How do you see this from the Faddeev Kulish is a corrector to describe S matrix. How do you see the electromagnetic memory from this? I think the question I'm asking is this vanishing? Is the fact that there is no soft, the leading soft factor, is it an artifact of the formalism or is it something physical? That
Okay. So yeah, I think it's because of the formalism. Because it's, I mean, as you said, it precisely says that there is no soft theorems.
For this.
Yeah, for this.
Yeah. I mean, naively that imply that there is no classical soft theorem also, right? That there is no classical memory or anything, everything will be gone.
Yeah.
But that's an experimentally, I mean, that's something you can presumably experimentally verify, right? Yeah, it might be worth examining how to get the classical limit from this. I mean, even using Faddeev and Kulish, right? There must be a way to recover the classical physics.
So you're saying by taking a classical limit of Faddeev-Kulish amplitude,
Yeah.
or
How to get the usual classical scattering results.
You would do that by what, looking at the Faddeev-Kulish dressing and saying that classically you would expect like an infinite number of soft photons or something like that.
Or just take the limit when the external particles are very have lot of charge, right? Then somehow the eddy probability amplitude will peak around some value, and that is the classical description, right? And in that description should agree with the usual Jackson's analysis. Yeah.
This drill states, because of this equation, it is probably not unique to solve particles.
Yeah.
Even in classical.
Yeah, I mean, what I'm saying that that's probably some a property of this formalism that physically it should give soft particles, right? Because
yeah, but even the formalism, I mean, kind of derived from the first principles, right? The Faddeev-Kulish states.
yes, the question is how to recover the usual classical scattering results, starting with this Faddeev and Kulish states. Right? It must be possible, right?
But doesn't it sound like the map between these asymptotic states and the classical configurations has become complicated?
But maybe it has become complicated, yeah. But that's a little surprising. Right? These are the physical states. These are the ones we should actually use for S matrix.
It should be very neoclassical.
Yeah, then one should be able to get the classical results easier from this.
But somehow these states have this radiation built in. So, a little like your universal classical results. Right? If you know something's coming out like this, you know there's some radiation associated with that. And that's part of the definition of these states, I have heard. That part of the radiation is included in this.
The definition
In the definition of the states, I have heard.
Maybe, but at least, I mean, you can put a detector and see that radiation.
So that is now in the dictionary. So,
Yeah, so maybe also be able to recover that
So,
using this dictionary.
but
yeah,
if
you would have to find the dictionary between usual Maxwell fields and these states.
Yeah, exactly.
so if this the cutoff in the Faddeev-Kulish states, so if that energy level it is of the detected energy level, then we can't really see the photons, right?
Yeah,
Uh,
but classically you can detect photons.
yeah, so I'm saying, so okay, if you think of taking a classical limit of these states, I mean this scattering amplitude,
Yeah, maybe as Siraj was saying that you have to now do some further work to relate this to actually what you see in classical experiments.
In fact, your results make it very natural to define a classical configuration with the soft photons included. Right? Just your classical results. Because you know that inevitably, if you've got something coming out and something going in, there's going to be some soft radiation.
Okay.
So that's a classical configuration labeled by particle momenta, but including some soft radiation. And it sounds like this should map to that.
Yeah, maybe. But if you do that, then the fact that it will actually switch on a detector becomes a quick map, right?
You'd have to understand how detectors interact with Faddeev-Kulish states.
Yeah.
Right, detectors are made of ordinary electrons without the message. No, I don't know. Yeah, right.
Why shouldn't detectors be made of the same states?
Yeah, why should
Yeah.
these are? Yeah.
Yeah.
Maybe because detectors are not. I don't know.
Clearly, these Faddeev states are built by knowing that there was this extra interaction. So they are built to say that I am taking this interaction already into account. These are new states. These are new states which I am scattering. I know that these states are nice because there was this interaction, which is the knowledge.
Yeah.
Yeah, it very explicitly produces the soft radiation, right? This extra term acts on the S matrix and produces the soft radiation. So somehow very explicitly includes that thing somehow, I think, in the definition of the S matrix.
So, but I mean here the cutoff actually sees the low energy radiation, right? So it clearly distinguishes the low energy and the soft. I mean that kind of a distinction is there, right?
So you will cut off at a very, very low energy.
Yeah, it is very low
And the
energy.
photons you detect are somewhat higher energy source. Yes. When you put the cutoff at the energy that is much lower than the photon that you detect. Then soft theorem will be usual soft theorem. Yeah, maybe that's what I want to conclude this. That you really absorb the very, very low energy photons in this for that reason.
Yeah, but it has soft photons also then.
Yeah, but very, very soft photons.
Yeah, very soft photons. Basically it kills only the soft divergences. I mean it can't kill any other divergence. It's just only the soft part of the scattering amplitude.
Okay. So is there a formalism in which you put a very, very soft cutoff
Okay.
and then recover the usual soft theorem from this formalism?
Oh, okay. I think so. Instead of the Faddeev states, if you consider a 2D dressing where it is the R out, it's exactly the soft photon. Then yes, I think you can consider those states, but those won't kill the IR. I don't know about the status of divergences in that.
What if you just push the Faddeev Kulish cutoff, the dressing cutoff, you push that to 0? That will do what you're saying, right? Which is that it only takes care of very, very soft.
Yeah, but you don't want to push all the way to 0
No,
because
no.
that will be by divergence.
Correct.
Yeah.
But that will be then a 2D dressing. I mean there won't be any integral over the momenta. It's just. But
Well, you can integrate over momenta, but up to a very, very small momentum.
so the momentum is not the limit going to. It's not going to 0, right?
So
There.
it is going to from 0 to very,
Some-
very small, right? That's what we include in the Faddeev test.
Yeah, that's what we include.
Yeah. And then if you look at the soft photons of energy a little higher than that, then that part is not included in Faddeev test, right? So you should get the usual soft theorem back.
Oh, okay. So then how to distinguish clearly the energy of the soft particle and the low energy particles? I thought that is also it is basically included in the Faddeev-Kulish. Can you really distinguish the soft and the low
Suppose
energy?
you want to look for soft photons of a certain energy. If it's,
Oh, okay.
suppose you want a soft theorem, but for photons of some particular energy, right? And then you can say that the Faddeev-Kulish cutoff is lower than that.
Yeah. Then
Then
that
you should
case
be able to get the usual soft.
theorem. Yeah, soft theorem. Okay, yeah. So then, that case, I mean, these photons, they don't really see the Faddeev-Kulish dressing.
Yeah.
Oh.
That they are not part of the Faddeev-Kulish.
Yeah. Okay. So, but in the usual construction, they are actually part of Faddeev-Kulish, right? The soft, or because they want to kill the divergence, right? So, which is coming from exactly from the
But
zero.
for that, you really need to include the very, very soft. Right? To kill the divergence, you only need to include the very, very soft photons. Whereas when you are talking about soft theorem, we are always talking about photons sort of something small but finite. Yes, I think it is probably possible to distinguish these two cases. The cutoff that you use in Faddeev and Kulish and the energy of the photon that you are interested in.
So you are saying although I have IR finite answers, but I can get usual soft theory for small but not
zero.
radical.
Yeah.
Even from this, because we have put
Seems
like it is possible.
but probably it requires some work to
Yeah, yeah. Yeah, then I mean in that case clearly this won't be 0. I mean then there is a possibility of soft theorems in this dress symmetries.
Why do you need this cutoff at all?
Okay.
What if the cutoff was the energy scale of the process?
So I mean my understanding is that if then so that it can't kill the divergence coming from the from a higher energy. So it can kill only that low energy divergences.
But presumably physically this soft production is correct until you reach the energy scale of the process involved. It's a momentum transfer scale or something like that. Right,
Okay.
you've got this soft production that accompanies this process that is physically correct until you reach some length, some energy scale which characterize the process. So up to there this thing is useful, beyond that it's artificial.
Yeah.
So what
But you can ask, is it like you want IR finiteness or do you want more than that?
I want to capture as much. Everything that's automatic from kinematics I want to capture in my asymptotic sense.
Okay, then you can integrate after those cases.
Right.
But even in the form,
Yeah, then you don't have the soft.
Fine, soft theorems, but I just wonder, please, for instance, what if I took the cutoff to be infinity? Is that a problem?
I mean-
I was wondering. It looked like 1 by omega. That looks quite tame as omega looks infinity.
No, but isn't that the integral?
yes, sir, but even so in the but in the Faddeev formalism, this cutoff doesn't come from any first principle. I mean, I think it,
Okay.
by hand we are,
To the scale of the momentum.
Yeah, but I was wondering whether you could just go all the way to infinity. Then you just introduce artificial unit.
it's,
Okay. Right.
Yeah, and probably what you want to do depends on how you want to use it.
Yeah.
If you want to include everything that's automatic, then you'll go all the way to the scale of scattering.
Yeah.
Right? If you want to see actually soft
Soft
areas coming out,
Yeah.
then you want to do something else.
And by the way, you should go on, but how a detector will react is really how charged particles move. And a dressed charged particle or an undressed charged particle moves the same way. Because the photons don't care about other photons. So that's in this phase part of the amplitude that she's not keeping track of.
That's true, yeah.
So you are just getting rid of this phase because you want to do a square, mod square.
Yeah.
This is the only reason. So that was more complicated. In the sense that this is not particle by particle.
Maybe you should.
Yeah, we have the wind till 4.
okay, so here I mean I wanted to say that the Faddeev states they satisfy the Ward identity. So with this condition, so I have started with I have started with the Ward identity in the Faddeev states. Then I just considered the action of the soft charge. So so which is just this equation, and I have shown that so the last two terms they vanishes because of the orthogonality condition. Then it just reduces to the commutators. So then one can actually compute this commutator. So basically Q soft is an operator which is linear in A and A dagger, and even R e power exponential of R out also. So then you can just compute the commutator. Then So I mean this is what you will get when you compute the commutator. So basically this Ki by P dot K, so this was there in the Faddeev state, this factor, and this limit EP going to 0 of EP, this is coming from the soft charge. And so this is exactly this the part of the soft part, which then so similarly one can find the action of Q hard on these external states. So basically since
Actually automatic. The fact that this word identity should now be automatic, I think. Sorry, is this correct? That it will just get 0. If you evaluate all the charges, you will just get 0. It should be automatic now.
But
Okay, sorry.
so I just want to say that okay, so if I didn't have this condition, then the word identity won't be satisfied. So basically I just want to give more importance to this orthogonality condition, because thing is I want to derive the these Faddeev-Kulish type of states in QCD from asymptotic symmetries. So then when I do that computation, I really I'll be just crossing over these kind of terms. So that's why I'm showing from here that this actually is 0, and
Unraised states, if you evaluate this word identity, you get a soft theorem.
yeah, it's soft theorem.
But now with raised states, probably this word identity will be automatic, like you will get say 0.
Yeah, that is true. So I'm just showing that the Faddeev-Kulish states actually satisfy the word identity. I'm not deriving the Faddeev-Kulish states from word identity. But I can,
QCD, that's what you
yeah, QCD, that's what I will do. So, but I can also derive the Faddeev-Kulish states from word identity, but then as I was saying, so these kind of terms will be there. So there is no point in, so then I can't, a priori I can't say that these terms are actually 0. So that's why I'm doing this computation, and then, so yeah, so the hard charge action. So since the hard charge consists of the matter current, and since in QED the photons don't interact, so then the hard charge acts only on the external state. So it won't interact with the Faddeev-Kulish cloud. So then the action is only just the soft factor. So then clearly here the word identity is satisfied, provided orthogonality, this condition is assumed, provided with this condition. Also if you consider word identity with multiple charges, then also one can see that the Faddeev-Kulish states, they satisfy the word identity, but there also you will have such a condition with 2 soft charges. Yeah, so as a summary, we observed that the Faddeev-Kulish states satisfy the word identity, and they also satisfy the orthogonality relation. Also then, keeping these observations in mind, we would like to derive the dress states in QCD. Okay, so I'll just explain about that. This is the soft charge for the non-abelian symmetry. So basically there is an extra color factor sitting here, and so the hard charge action is Q hard acting on the external state, it's just the soft factor, and basically there is also a TA, there is also a matrix sitting here. So then the action is in such a way that this matrix rotates the color of the external state. So it's just like this is 0, so the action can be given as follows. basically this S0, just consider a state with momentum k and color index b. So then this S0 will just rotate the color index in this way. Yeah, so that is the action of this q hat on the external states.
And the thing in the bottom is what appears in soft theorem.
Yeah, this is soft factor. So here, Ki's are the moment of the external particles.
So the only extra part is this TAKI.
Yeah, only this is. Okay, also in QCD, since the gluons interact, the Q hat will have gluon current also. So the external states can have even gluons also, hard gluons also. So then to find the dress states in QCD, so basically we start with the following assumptions. One is the word identity. Then the second one is that the soft gluon modes, they satisfy the orthogonality relations with respect to the asymptotic states of the theory. Yeah, so then with these assumptions, so I'll start with an ansatz for the dress state. So if you just see that, yeah, so this operator, this is basically, it is linear in the creation alienation operators, and Q is the gluon momenta. So this is also a coherent state of soft gluons. So here Ki are the moment of the external particles. So basically we want to find this n mu using the word identity. And yeah, so there is an extra, there is a, this PE denotes the energy ordering. So basically which says that since these are matrices, so if you take a second G square term in this state, so this will have this form where Q1 and Q2, they are ordered in energy such that Q1 is much greater than Q2. And so the thing is, in QCD, word identity can dictate only these kind of states.
Why, or is there a physical reason why you have energy ordering?
Okay. So from word identity perspective, the thing is that so when you just take the commutator of the Q soft operator with this state, so then since these are matrices, so then to look like an eigenstate, I mean it has to have such an ordering. So otherwise,
You have a reverse ordering, definitely doesn't work.
yeah, reverse ordering will also work.
Reverse ordering also.
Yeah, but reverse in the sense you meant this Q1 and Q2, right? Or yeah.
Instead of ordering increasing energy, you do decreasing energy.
Yeah, that will also work. Yeah. If there are no energy ordering between the gluons, then word identity can't really pin down these states.
So NA is that soft factor?
Yeah, NA will eventually turn out to be the soft factor.
At the moment,
From no, arbitrary. And yeah, right now I'm just assuming this form, I mean from the QED for the Kulish states, so that's why there is a cutoff E also. But I can explain why this cutoff is coming here from asymptotic symmetry perspective.
I have a question. Okay. So if you write the exponent in position space, you need to take care of the ordering, right? I mean, could you give me some physical intuition how it should?
Oh yeah.
She's defined the exponent to be ordered in some way.
I mean, position space, that will also imply some ordering.
Oh, I see.
So I'm trying to understand it from position space. If it's a valid question at all.
So I really don't know about the position.
Actually, sorry, I'm just going one quick. The final answer up there, color indices are contracted. So
Yeah.
the ordering is only because it's an operator.
Yes.
Now, amines and different momenta commute with each other or not?
A mu's.
A mu and A mu, the commutation relations are the usual ones. A mu
Yeah.
Q with A mu dagger Q prime.
So it will have a delta AC just for the color index, just that.
Delta Q minus.
But also delta Q minus Q prime.
Yeah, delta Q minus Q
So
prime.
then if things at different energies commute with each other, why do I care how it's ordered in energy space? It's only at equal energies that you have to worry, right? Or not?
But N's will also have color or no?
N's will have, N has color.
It has
It is,
color matrix.
it will be a matrix actually. N is a matrix.
But in the end, the A index is contracted. So the whole thing on the top is just some operator, right?
Yes.
So what for even NA, right? It's an operator, it's a TA, it's like T.
It is TA. It has a TA in it.
Okay.
So that two successive TAs which are not common.
I mean, but
This is a PI and not contracted.
I thought there were no indices left, or are there? Sorry.
One independent, one fundamental.
Oh, it's a matrix. It's a matrix. Matrix as well as a TA.
Yeah.
So that object is not a number. It's a matrix.
yeah. But I mean, this TA is actually sum over the external states. So then the external states are they are in a different space, right? So then they actually commute in that sense.
But if you have multiple, you have an exponent.
Yeah.
Exponential, right? When you expand it out, then they are acting on the same state, right or no? The
Okay.
TAs,
So TA has the index. I mean, it has the index about the external state also. So TA is basically TAKI. Yeah. So TA is kind of TAKI. So KIs are the external states. So then it acts on the external states, right? So then basically then. Oh yeah.
Go back to the previous slide, right?
Yeah.
You had this matrix TA.
Yeah. You're right.
Yeah. So these will act on, there are successive operations of this TAs, right?
Yeah. There is a yeah.
So they are the commutations in matrix.
So, but then you need to say how the T's are ordered. And can you go back?
But I think what she's saying is that the T's are related to, I mean, tied to K, right? For a given energy, there is a T.
Okay.
And the T's are ordered according to the energies that they carry.
Okay, thank you. Yes.
Yes, because its ends are ordered here.
I see. Thank you. Thank you.
Yeah.
It looks a little artificial. I mean, okay, maybe there is a reason to do that, right? But at least,
It's
well, normally in physics, you don't see energy ordering, right?
Yeah.
So it looks a little strange.
Okay, so I mean basically in QCD, so these kind of states they kill the divergences which are energy ordered. So it's like.
Is it that the soft limits are like consecutive soft limits?
Yeah, consecutive soft limit.
Then you take one energy to 0 parts. And
Yeah, then the second one.
They don't come. But with this ansatz, you will eventually show that it satisfies the variety.
I mean, so the thing is, this will satisfy the single bond identity, but this won't satisfy the bond identity with two charges. So that is precisely because of the contact term. Yeah. So one can just use the bond identity, then. Yeah, the soft part, you can just do the, by assuming the orthogonality conditions, then the action of soft charge, it will be just the commutator. So then this will just pin down this n mu's from the dressing operator.
So in that, in getting this relation, have you used the fact that it was energy ordered?
Yes, because otherwise I can't really write in this form. Yeah, because if those are not energy ordered, then I can't write in a closed form.
And that has something to do with the fact that you have to take the limit of EP going to 0. That's what the energy is entered in, right? In this EP going to 0 limit.
Yeah. So, so there is an energy ordering between this state as well as between this state and the Q, between the P also. So I am taking P to be the softest. Yes. And so then similarly one can find the action of the hard charge, but here the thing is the hard charge, it acts on the dressing also, but for the time being I am not taking that into account. I have just considered the action of the Q hard only on the external state. Yeah, so basically with this assumption the Ward identity will reduce to just this form. Then there is an extra, there is a TA, basically there is a TA color index here. Then so from here, by assuming the S matrix elements are node 0, one will get this constraint for the n mu's. And yeah, and using this constraint one can actually, so this dress state, this will eventually reduce to this form, and this is precisely the soft factor.
Uniquely determined, or is there any freedom?
Yeah, because I mean this choice, there are infinitely many solutions here. So this is just a, so I can choose, so basically this n mu, so S0 there is a sum over all the particles, right. So then I can just choose n in to be 0, then n out will be just sum over all the particles. So that will give me some other dress state.
But when you take two charges, two of them soft, that is some known
Oh, okay.
theory.
Yeah, I'll just come to that.
To match that you might need to adjust what kind of dressing you want.
Yeah, that is true.
So your highest charges, were they to the right or to the left? The highest energies?
Left.
To the left.
Okay, so then the thing is for this operator and for the two operators, I will be taking the energy ordering to be different.
I see. So I see. So you first act with the lowest charge, the lowest
Yeah.
energy, and then
So I am taking the Q soft to have the lowest energy.
I see.
By definition, that's the softest.
That is the softest. That is what I am taking. Yeah, so then this state, so this is like the Faddeev state. So okay, I want to say one more thing. So then the Ward identity, so it can actually determine only the low energy behavior, the behavior of this n mu's at soft energies. So basically in general n mu can have, okay, so this expression says that n mu has to have a pole in EP. Because S0 has a, okay, so there is a EP sitting here, so then which says that n mu has to have a pole in EP.
what I could get,
So I am saying, so this the expression says that n mu, it has to have a pole in EP, soft momenta. So the thing is then Ward identity can determine only the behavior of the states at soft momenta. So in general n mu can have maybe log correction is also, log omega kind of term, but those terms, those will not come from Ward identity.
Okay. So only the one over omega pole
Yeah.
you pick up.
Yeah. So then to explain about the cutoff also, so basically I am just making a statement about, so the subdominant, the other terms in n mu, those will be subdominant in this, within this energy level. So basically that is how the cutoff comes into picture from the Ward and asymptotic symmetry perspective.
Any photon that's not, any gluon that's not in the cutoff region is considered a hard gluon, right?
Yes.
Okay, so now changing the cutoff is a little more interesting because you're increasing or decreasing the number of hard gluons by changing the cutoff.
You could also put an exponential factor. Instead of putting a sharp cutoff, you could put in something like 2 minus lambda e.
Okay.
That will also do the job, right? So because from here what you are saying is that you only get the this limit is what is determined, right? So you multiply n by e to the minus lambda times c. Then in the e goes to 0 limit, that is 1 anyway, right? So that's also equal to.
Oh, okay. So you're saying for this
That is in n
some phi function where phi is
e to the minus lambda.
okay.
Instead of the sharp.
Okay.
Right? This will also have a cutoff. I mean, this will basically cut off at e equal to 1 for lambda. Right? You don't need a short cutoff.
So, but the Ward identity, this S0 is coming from the hard charge, right? So then how do I?
See, because as
know
e goes
that?
to 0, so left hand side includes only the e goes to 0 limit, right?
Yes.
So in that limit, this is 1 anyway. Not affect the sign.
Yeah.
So,
Yeah, that will also do the job. So then one really won't get the Faddeev-Kulish dressing, right? If you do the same analysis in QED
I think the same thing you could probably do in QED also, right?
with the integral.
Yeah, just multiply by some e to the minus lambda. Will anything go wrong in Faddeev Kulish to use some exponential cutoff instead of a short cutoff?
Since Faddeev Kulish works with any cutoff, then you can integrate.
That's true, yeah. Yeah, this is superposition of
Yeah.
But actually, what does this buy you if you use a smooth cutoff?
What is it?
What does it buy you? I mean, like,
Why is it?
because for e goes to 0, EP goes to 0. Anyway, this guy is becoming 1, and that's the only thing that the asymptotic symmetry can fix.
Yeah.
Do you mean that if you have like subleading?
Yeah, but very normally smooth cutoffs are always better.
Of course, yes. But I'm saying in this particular context, is it going to?
Yeah, I think the infrared, as far as the infrared divergence is concerned, it will probably not make any difference. Right? You could smooth cutoff and sharp cutoff will be the same.
At EP goes to 0.
Yeah.
But the finite part will be better somehow.
Yeah, finite part will be better.
Okay. So, but then this stress state, so if you consider Ward identity involving multiple charges, so then this state will not be consistent. That is precisely because of the contact term, as you were saying. So basically, if you consider the Ward identity involving two charges.
So in unrest states, if I evaluate this, then I get multiple soft theorems.
Consecutive soft theorems. So if you assume that one of the momentum is soft here, I mean softer than the other, then you will get the consecutive. So I am assuming that also here. Yeah, so then if you consider the Ward identity with two charges, so basically, yeah. So then this term, there will be a term where there is a commutator involving Q soft and Q hard. So this term is, so this will just give S0B some QC. So when you act this on an external state, so this is precisely the contact term. So this will capture the one gluon being emitting from the another gluon. So maybe I can just write down this also. So it's basically S0 AC, then QC. So then when this QC acting on an external state with momentum K and color index D, so then this will produce a soft factor, Q soft. So then this is precisely so this term is exactly characterizing this kind of interactions when one gluon is being emitted from the another gluon. So yeah, so then because of the presence of such terms here, the word entity, so in the dressing we got, so there was no term which characterizes this kind of interaction, the gluon-gluon interaction, and because of that, so the double word entity will not be satisfied. So then if you take 3 gluons, then there will be these interactions which can't be get from these interactions. So basically then if you take further, then there will be more complicated structure. This so this is the most natural modification to the ansatz. So this will include, inside this exponential there are exponential number of terms. So then so here, yeah, so these all n1, n2, n3, those are basically matrices, and you can use, basically we will use multiple word identities to determine each of the terms. So
And it doesn't end. You have to keep adding.
one can use recursively each one. So then so then this n1 will be just the singles of gluon factor, then n2 will be precisely this contact term, then n3 will have sum of the two, like
Closed algebra of these charges?
no,
The algebra does not close.
it's actually exponential of exponential series. So then to get all these n1, n2, n3s, one can actually use multiple word identities at each order, then as I was saying, the orthogonality condition at each order in the coupling. So basically if you just consider the single word identity, then single word identity can pin down this n1, then using that n1, using the word identity for 2 charges, one can get the n2. Just you can do the procedure and you can just find all these n's.
If you do it in gravity, then the charges have a closed algebra or not?
Yeah. So if you take the leading charges, yeah. No, gravity it is closed. The algebra is closed actually.
So there
Because
is
they are a contact term for the leading order.
Yeah, there are no contact terms for the leading. But with the contact terms,
I think subleading order has only 2-point contact terms, but no higher contact terms. In that sense,
it is
gravity
closed.
probably simpler.
Yeah, it is simple.
So in gravity the statement is that this will close, the algebra will close, and therefore one will.
Yeah, I think as long as you are going only up to subleading or fixed order and thing.
Let's say leading order.
Yeah, in leading order there is no
There are no contact terms in
So
gravity.
that should just be very simple.
Yeah.
That is just like QED, just the QED.
Physically, that is because very low energy gravitons don't want to radiate
Right.
due to
Because
thrust
I-
as dimension.
High derivation.
Yeah.
But what is surprising is that in QCD there is a closed form. I would have expected.
So these states actually they have, I mean Catani and all they have predicted these states. I mean they have, so even they have derived these states from the Faddeev type of construction also.
But when we actually directly do soft theorem analysis in QCD, you don't find a closed form.
No. Because, no, we won't. And I mean regarding the energy ordering, so from the word identity, if you take the double word identity, so then, so I don't know about the multiples of theorem, but if I use multiple word identity, simultaneous word identity, then probably I will not get the energy ordered form. So it is because I am taking the consecutive word identity, that just tells that these are ordered. So I hope
There
that.
may be different way of writing it, which doesn't require energy ordering, but the coefficients may be different. Okay?
But even the energy ordering, so if you take the simultaneous word identity, then there is no ordering basically, right?
But the Faddeev Kulish should be unique, right? I mean, whatever, then it should be, once you have written the Faddeev Kulish tracing, then whichever way you take, whether you take consecutive or simultaneous soft limit, it should always give the correct result, right?
In QCD or?
In QCD, yeah.
So that actually I don't know, because if you take the double word identity, it involves nested commutators. So then if I don't specify the ordering between the charges, then I really don't know how things work.
If you take your cutoff to 0, do these higher order terms become less and less important? I mean, it seems like there's less and less space for these multi-scattering things.
But I can still have multiple gluons which are, I mean, lower than the, yeah.
You can have them, but if they all have to be very low energy, then there's not so many ways it can happen.
But I think each of them probably will always a divergent. There are multiple integrals. Right? And I think there is a logarithmic divergent integral. So even if you make it very small, you still get, you will not go to 0.
Okay, fine.
Just to be totally sure, in gravity, if you calculated this commutator in soft analysis, it is 0.
I think in the leading order, because this is all at leading order, right?
These are only the leading charges.
There it will be 0. And okay, this is one answer. Second thing is, if you take these states and really compute using Feynman diagrams order by order, is it the claim that all of the divergences in the order?
I mean, so, this will not kill the collinear. Even in the Faddeev construction, so even in QED, they have not computed this amplitude. So they just showed that the divergence will cancel. I mean, they didn't show that what is remaining. I mean, they didn't compute the amplitude. So, I mean, we don't know the Feynman rules for the Faddeev states actually. So also this will not kill the collinear divergences. So basically in the paper by Schwartz, so in that paper he is actually computing the scattering amplitude, the IR finite scattering amplitude.
Using Faddeev.
Yeah, it's not exactly Faddeev states. Okay, so in
those states also pure collinears.
sorry what?
The states that he is using, probably they pure collinears.
So basically for him, so the Faddeev S matrix is, it's actually basically these omegas are the molar operators. And for the Faddeev-Kulish, this omega plus is let's say e power I h t yeah, so I mean, so in the usual case, so this was H0, which was just the free Hamiltonian when you just define the scattering amplitude. But in Faddeev-Kulish, so basically he said that it is not the free Hamiltonian, it's the interact this, it's actually Hi, the interact Hamiltonian, which is the, I mean the interaction which survives at infinity. So this was the Faddeev-Kulish construction. But then in Schwartz, their way of doing, basically they are taking this Hamiltonian to be the Hamiltonian of soft collinear effective theory. So in that way of doing, I think for them, the collinear and the soft, they just factorize and they are showing that it actually cancels. I mean their dressing is not, so in QED their dressing is, I mean same as Faddeev-Kulish, but QCD it's different. Yeah, so okay, I'll just so there is one more point I want to say. So yeah, so regarding the action of the hard charge, so while doing this, I was assuming that the hard charge doesn't act on the dressing operator, but since it is gluons, so the hard charge will have gluon current, so it can act on the operator also. But then if you do an analysis in the Wadent in the coupling, so then basically you will not see that term. It is always a higher order in the coupling. So that is, I mean in that way we won't really see the action of Q hat on the dressing. So then there is one more argument you can say. So when this Q hat acts on the external state, so basically it actually rotates the state. So then this dressing will be different. It will be rotated dressing. So then, so actually when you do this analysis, you will have this, which is a new dressing, then the asymmetrics, then here also you will have a dressing. So basically, so one argument is that this state dressing will be different. So then it won't really kill the IR divergences. So then this scattering amplitude just vanishes. So with this argument also one can say that the action of Q hat on the dressing operator doesn't really come into the picture. Yeah. So the states we get.
One Faddeev state cannot decay into Faddeev plus a soft photon. Is there a statement like this that you said? What did you say? Did you say an
So it's actually.
The seminar room is free or?
No, we have a couple of
No, it's done actually. It's fine. So yeah. So these states, so they have already identified in the literature by Kattani and Ciafloni, and they have shown that such states, so they emerge from the Faddeev-Kulish approach of approach in QCD, and they have shown that the asymmetric elements in these states, they are IR finite. Yeah.